We're going to talk about Stokes' theorem on this slide. So Stokes' theorem is going to provide a connection between line integrals and flux integrals. You can think about this as a strong version of Green's theorem. These things could live in 3 dimensions. Oftentimes we'll think about them, we'll apply them in just 2 dimensions because it applies to that as well. From the last section, we talked about curl and circulation density, and we're going to need a connection between the 2 of those. If I take the curl of F and I dot it with a normal vector n, that's equal to the circulation in the direction of n of that vector field. N is not necessarily the direction that the curl is. It could be a different direction. Okay, so here's the idea of Stokes' theorem. First, I'll start with any surface S, and this surface could potentially live in 3 dimensions. So I'm imagining some surface down here that maybe it looks like a bowl or something, and that surface could live in 3 dimensions, as I said. And around that surface, I want there to be an opening, and I'm going to call that opening the boundary. So notice that boundary forms a path, and that ultimately that path is going to be the closed path C around which I'm going to integrate, and the red surface is the surface through which I'm going to consider the flux. Okay, so the first step is to take this surface, and it's going to be a little bit difficult for me to draw this, but take this surface and draw a grid all over the surface. Okay, so you're drawing little squares all over the surface, and around each one of those grid squares, calculate the circulation. That is, calculate the line integral of the closed path around each one of those squares. So we'll call that the line integral around C sub I of f dot dr. That's a line integral. So to emphasize that this is a closed path, I'm going to put a little circle around that integral. Okay. Now if I take every single one of these line integrals over the entire surface and I add them together, all the edges that are touching inside the surface, their contribution to the overall line integral is going to cancel. And in the end, what I'm going to get is just the contribution around the boundary C. Okay, we're going to need to be very careful about the orientation of everything, but I'm not going to worry about that right now, and we'll talk more about that when we do an example. For now, think that as I add up all these contributions of all these small circulations around these squares due to cancellation in the end, I get the line integral around the boundary. Okay. Now, let's just focus on one of these line integrals around one of the grid squares. Okay. So if n is a normal vector to one of those grid squares, so let's say I draw a normal vector there, then the definition of the circulation that we studied a section or 2 ago says that, remember, the circulation was roughly the line integral divided by the area of a square that formed the interior of that line. So circulation was line integral divided by area, and when I let that area go to 0, that's when this approximation became equality. So here, I've simply multiplied by the area of the interior of C. The circulation around one of those squares is, the line integral on one of those squares is the circulation of F times the area of that small square. Okay, and then the connection between the circulation and the curl that I put on the first slide says that this circulation is equal to the curl of F, that's a vector, remember, dotted with this normal vector, the normal vector to the little square n times delta A. Okay, now what's going to turn out to be important for us throughout these examples that are to come is that n dotted with delta A is then a vector. It's a vector delta A that's pointing in the direction of n. Okay, so when I rewrite it that way, what I get is that the curl of F, or I get that this line integral around a small square is the curl of F dotted with dA as a vector. Okay, take this, that is that, plug it back in there, add them all up and let the appropriate delta A's go to 0, and what you get is Stokes' theorem. So Stokes' theorem says that if I want to evaluate this line integral around the boundary, I can alternatively do that by taking a flux integral where I take the curl of f, this is the vector curl, and I dot it with dA. And dA should be the dA that corresponds to the surface, and I do that over the surface. So initially this might seem like a crazy thing to do, but let's look at a couple examples and see how it plays out. Here's a first example, and perhaps the hardest part of this example is going to be to figure out what's going on. So our goal is to calculate a line integral. The vector field is given by this, and the curve C is the upper half of a circle, x squared plus z squared, sorry I made a typo there, z squared equals 9, in the plane y equals 0, and then I need this to be a closed path, and so I'm going to close this off along the z-axis from 3, 0, 0 to minus 3, 0, 0. And I'm going to go around this path counterclockwise when I'm looking at the path from the positive y-axis. So first, let's just think about what's going on here. So this path is a circle in the x-z plane. So it looks like it's a semicircle of radius 9. So I'm going up here. Radius 3, x squared plus z squared equals 9. And then I'm going to connect the semicircle between the point minus 3, 0, 0 and 3, 0, 0. Okay, so in this case, the y-axis is coming out of the screen, and so when I look down, I want to go around this path C in a counterclockwise direction. So I want to orient the path going in this direction. Okay, so we're going to leave that for a minute and go on and think about what it is that we're going to need to calculate. This is Stokes' theorem, so eventually, let me write down what we're going to evaluate. We're going to evaluate this line integral by evaluating the integral of the curl of f dotted with a dA vector. Okay, and we're going to integrate over the surface S. So first, what is the surface S? Well, the surface S is the interior of this curve. So notice in this example, this surface is not 3D, it's 2D, but that's okay. It all collapses down to 2D just as well and perhaps even easier. Okay, so the first thing that I'm going to need to do is I'm going to need the curl. I'm going to need to know what the integrand is. So let's calculate the curl of f. We'll use the determinant definition, or the way to remember it. So we write I, j, k in this determinant, and then we have partials with respect to x, with respect to y, and with respect to z. And then in the bottom row, we have x plus z, x, and y. Okay, so let's see what this determinant is. So for the I component, I get the partial of y with respect to y minus 0. So I just get 1 I plus, in the j direction, this partial of y with respect to x is 0, minus the partial of x plus z with respect to z, so that's 1, so I get minus 1, but remember I always have an extra minus in the j direction, so we get plus 1j. And finally in the k direction, ignoring k's column, this partial derivative is 1, minus that partial derivative is 0, so I get plus 1k. Okay, so the curl of f is a pretty simple vector, I plus j plus k. Okay, next we need to think about what dA is. Okay, so dA is going to be based on a small grid square on the surface, which is in the xz plane. And now is the point where we need to think carefully about the orientation. So here's how the orientation works. It's determined by the curve whose direction was given. So imagine a point very close to the path C, and then draw a circle around that point in the direction that agrees with the direction of the path. Okay, now use the right-hand rule, so wrap your fingers around this circle in the direction that your thumb points in the direction of the orientation of A. Okay, so in this case, your thumb points out of the screen, which is the positive y direction. So dA is going to have an orientation of j. Okay, so that is the surface is oriented in the j direction. And each one of these grid squares has a dimension of dx by dz. Okay, so dA will be dx dzj. Okay, so maybe I'll try to squeeze in what this integral looks like, and then we'll evaluate it on the next page. So this integral should be equal to a double integral, because I'm going to integrate dx dz. So I'm going to take this vector and dot it with dA, and notice that I'm only going to pick up the j piece, so all I'm going to integrate is 1 dx dz, and I'm going to integrate this over, I'm just going to draw a picture to represent this, over the semicircle. So actually it's a little sloppy, but I think I can fit it all in on this slide. Notice, as we've seen before, the integrand here is simply a constant, just the constant 1, and so this double integral simply represents the area of this semicircle, and we can just use geometry to calculate that. So it's 1/2 of the area of a total circle of radius 3 squared, and so what do we get? 9 pi over 2. So 9 pi over 2 is, in the end, the value of this line integral around the boundary of the semicircle.